Wasn't on tape. We burn the tape. All right, here this is a big day for physical methods of control. Wednesday will be a big day for chemical methods of control. So this is, let me get to the correct PowerPoint. I'm just buzzing in. This is the one, since it's a textbook one that you folks have. I mean, I didn't see a whole lot here. We talked about the different targets and stuff like that. To me, I don't ask you about those things. Down the road, could somebody in nursing or someone else want to know, like alcohol specifically targets cell membranes? That's why it's not particularly effective, because particularly for like, it works for enveloped viruses, but not particularly well against almost anything else. And yeah, I mean, it has limited activity, but that's its big. And we will, as we go through these, I'll comment on them. I'm not going to have you recollect them unless it's something very specific, and I will tell you that. And they're just talking about what it's doing and surfactants and stuff like that. And we get into that a little bit more because we'll talk about chemical methods of control Wednesday and perhaps finish it up on Friday. And they just give you a little nugget about alcohol, and it certainly became very popular. We utilize detergents all the time. We will get to that. And if you're looking at antibacterial soap, it's got detergent in it. But we'll get there. So, and iodine, the question was, it's again, it's an antiseptic, not a disinfectant. That's all coming. So this is all about heat and physical methods of control, principally heat and radiation. We utilize, as much as possible, moist heat, steam, okay, boiling water, those kinds of things. Still very effective. We'll define how things sterilize and how they don't sterilize, etc. The beauty of look, it's tiny. Water is a teeny tiny molecule, H2O. There's not much to it. It gets through everything. I mean, it basically everywhere in our body is pretty much permeable to water, with very, very limited exceptions, anatomically speaking. And the same is true for almost any living thing. So when we use superheated steam, what it does is it's very efficient. You can have normally, for instance, if you look up there, it says dry heat. Why don't we just use an oven to sterilize things? Well, two reasons. One, it's pretty high temperature. So you have to crank things up to somewhere between 200, maybe 350 to 400 degrees Fahrenheit, 170 to 200 degrees Celsius, roughly, for a couple of hours. And if you want to put, and you could do it, you could sterilize, if you had instruments you wanted to sterilize at home. You want to sterilize for whatever reason your silverware at home. Why, I don't know. Dishwasher, fine. Put them on a sheet pan. You couldn't touch, couldn't stack them, anything like that. You put them in and shove them in there for an hour and a half to 2 hours. Take them out very carefully because they're super hot, and you'd have to let them cool down in such a way, hopefully, that by the time they cool down, they're already starting to get contaminated. Is it used? Absolutely. Have I seen it used in offices? No question about it. They have it. You can do it with a toaster oven, for that matter. But, and I remember a mentor of mine actually had a little toaster oven gizmo that he did a lot of sterilization with. Long story short, the problem is you can't stack them up because the heat doesn't penetrate. Dry heat doesn't penetrate. You ever take frozen French fries and put them in the oven? If the French fries are on top of each other, you get mushy in the middle. You don't get crispy. I have an appreciation for crispy French fries myself. Okay, it's absolutely true. We use moist heat because it penetrates. In a hospital, we will take, the 100 or so instruments that just got used in a surgery, make sure they're clean, talk them in, after they're clean, you put them into a metal container, a stainless steel container that's got a whole bunch of holes so the steam can come in and out, and just throw them in there and you throw them in the sterilizer. Period. Don't have to wrap them, don't have to do anything else like that. And conceivably, they would sterilize. Doesn't matter whether they're in contact. That contact, no matter how close it is or how many, you'll get through it. We would sterilize gauze pads. We put a stack this high. It gets through. Perfectly permeable to all of that stuff. That's the beauty of moist heat. It's easy. It's cheap. Everybody can do it. You can do this at home because effectively what an autoclave is, a steam sterilizer, is a pressure cooker. I mean, I could do it with my Instant Pot at home anytime. Put whatever you want in there the right way. Put some water in the bottom. Crank it up to half an hour. Just be careful. Seal it. Set it and forget it, so to speak. So moist heat, we can utilize hot water, doesn't sterilize, boiling water, doesn't sterilize because it doesn't take care of endospores, or steam between 60 to 135 degrees Celsius. You're going to see there's a number I put up there is the number that's accomplished, whether it's in the autoclave at the hospital, preset, or whether it's in your Instant Pot at home. 121 degrees Celsius is 15 in a sealed system. 15 or 20 minutes, the pressure that it will be in that system is 15 pounds. Number to remember. Because remember, all of this is based on one thing, that pressure and volume. The famous equation for the ideal gas law. When we get an A and P to respiratory, everything is based on it. Okay? And so you're in a system where the volume is constant. You're in a sealed container, and as you raise the temperature, it will, because the volume is not going anywhere, the pressure will go up. That's the whole idea. You don't have to know that chemistry. I'm not holding you to the ideal gas law, despite my affection as a chemistry major for that. Sorry. Old habits die hard. But effectively what happens is you crank up the heat, the pressure goes as well, and that pressurizes or superheats the steam. I mean, when water boils, it goes to 212 or 100 degrees Celsius, right? When you put it in a pressure container, it's called superheating. You can do that in a microwave. In a microwave, did you ever have, like, you get like a glass container, like a Pyrex, and you're doing a recipe, and you got to heat the water for a certain amount of time, you stick it in there. Pros put a glass rod in there because of the surface tension of the water. If they take it out without that glass rod to break that top, it'll all of a sudden, you drank it out too fast, it's all over your hand, and it's a big time burn. So they put the glass rod in to relieve the surface tension, which doesn't allow it to superheat. That's just it's what chefs are taught to do when they use the microwave. Yes.
So would that be?
Beg your pardon?
Would that be like part of moist heat?
Yes, absolutely. That dry heat's over there. Everything else up here is moist heat. Pasteurization, which I introduced before, is a method of disinfection. That's for sterilization. It's a method of disinfection here. Okay, and disinfection, this is the original method, Pasteur, the wine, etc., 62 to 63 degrees Celsius, depends on the author, 140 degrees Fahrenheit, like I told you, that's the interior of your dishwasher, for 30 minutes. Is it still used? Absolutely. The trouble is when you talk about pasteurization at a big dairy like Land O'Lakes, that's a lot of time. And in business, time is money. If you have a giant batch and a giant sterilizer or a giant pasteurizing unit, 30 minutes is a lot of time because even if you run them continuously, you can only get 48 batches in a 24-hour day if you work around the clock. So they developed what's called the HTST, or a high temperature short time method. It's on the PowerPoints. 72 degrees Celsius for 15 to 20 seconds. Bang! And these machines crank that temperature up with the steam, effectively superheating it rapidly and injecting it into the system. And in 15 to 20 seconds. So the next time you get a thing of half and half, a thing of almond milk, whatever product you're looking at, that's basically how it's pasteurized commercially. If it's got a lot of fat content, we have to crank it up another 10 degrees, okay, for about maybe double it, 20 to 30 seconds time. Fat content is hard to penetrate, so think ice cream. Heavy cream. That kind of stuff. And then this is the oddball, and this is more relevant till we get to chemical methods of control. It's called ultra-pasteurization, erroneously. It's known as the ultra-high temperature method. You're going to see that on the Nestor PowerPoint in detail. And what it basically implies is this ultra-high temp method, not pasteurization. You call it ultra-pasteurization, which is not. They literally are sterilizing the inside of the container and superheating the liquid that goes in there. So the next time you get a juice box, okay, the next time you go and get one of those neat little things you can put in your coffee with a peel off and pour them in, if you go to, Get Go or one of those, they used to have them all the time in sheets, but they don't have them anymore, okay? all of those are here. I mean, when we have events over, like catered events over at the event center, they just have half and half in those little peel-off containers. Those are all ultra high temperature. Basically, they use superheated hydrogen peroxide in a special container, immediately inject only for a couple of seconds because it evaporates so quickly. Put the liquid in and seal it. I've seen it. I've actually seen the machinery done that. I went to the science center in Toronto. Fascinating. And they had a whole, like, they typically dedicate the third floor to some big demo. If you do travel up there, that science center is just brilliant. It's not part of the science center. If you remember, here at our science center, it doesn't get you in there, but it's a worthwhile trip. Kids love it. They have all sorts of hands-on stuff that they can do. That was a go-to for us, like every other year when my kids were. None of them really cared about science, but what are you gonna do? They like going to the zoo and the amusement parks after. Go figure. Sure. Okay, so back to where we started. So moist heat, steam, dry heat. Everybody, I'm giving you this. So you use dry heat every lab. You're incinerating your loops. That's a classic way to sterilize. How do we get, if you have hazardous waste, that is incinerated. If you're a veterinarian, you have animal carcasses, they are incinerated. So that's it renders whatever left sterile and not potential for disease holding. So moist heat, lower temperature, shorter exposure to achieve the same effect as dry heat. Okay, and it works by basically denaturing and coagulating the proteins. Remember we did this, AP1. Okay, what happens when you denature a protein? That's the beauty of heat. Okay, when the optimal temperature for the protein or any living system, and it's the death temperature very close to each other. So that's when we get a temperature, our proteins start to denature, particularly enzymes that conduct all the business in our bodies. That's why temperature is such a big problem. When you have a sustained high temperature. So that you should be familiar. Dry heat, okay, all that gets rid of the water, denatures the protein, it incinerates, the best word. Okay, and again, initially it can make this change. So that's why you need very, very high temperature, typically oxidizing the cells, or if you're thinking about the oven, that's more of the stability potentially being increased and requiring that higher temperature. And again, longer amounts of time because you don't have the penetrating power. That's very significant. It's there, they're just showing you, to hear all of the kinds of things that can happen, changing its shape, finally blocking active sites, Because again, it's mostly about enzymes. A couple of examples. Moist heat, the classic, 121 for 15 minutes. Some authors will say 20, that's fine. This is an interesting one. In a hospital operating area, even though you'll have a lot of forceps, tweezers, pickups. You'll have a lot of retractors, you'll have a lot of scissors, you'll have a lot of hemostats, but for special instruments, you don't have that many. They're very expensive comparatively. So it's not unheard of. It doesn't take much for one of them to become inadvertently contaminated. So if this is the sterile field, and for whatever reason, with anesthesia, let's say arbitrarily, not that I'm expecting it to happen, this falls off out of the field to here. At that point, it's no longer sterile. It has never been touched, other than by sterile hands, sterile equipment, gloves, etc. But once it's off the field, by definition, it's not sterile. If it's a critical instrument, it may be necessary. So whoever is doing the procedure will say, please get this flashed. And so we call that flash sterilization. One of the circulating personnel will grab that they'll have a central area. Most of the time, if you're in an operating room, they're all around like a perimeter in the central areas where they do sterilization, make up packs, bring stuff in and out, etc. Leaving the operating rooms like that. So you might be a big hospital, 15, 18, 20 of those. I'm trying to remember how many I always had. West Penn had about 18 of them. I remember being operated on there. I was just, I was curious. And what happens then, they will take that, put it into the flash, which they already have heated up, close it 3 minutes in there, pressurized steam, take it out, put it in a basin, fill it with like sterile water, sterile basin with sterile water, sterile saline, whatever, to cool it off and get it back to surgery. That's the way. And then the trouble is, if they drop, it's not so easy to do. And if they got stuff on them, it's not so easy to do. So typically, you're reserving that for instrument that really has not been significantly contaminated, but you want to assure yourself of the sterility. Those are, again, little nuggets that might be of interest to you down the road when you start to do rotations in OR, etc. And you can see the dry heat. I mean, we're talking 10 hours at 121. Now, I mean, I think that's a little conservative at 170 or 350 degree oven. I mean, that's why I crank them up. I would say take it to 400 if you're using your own oven. The extra time isn't a big deal because it's not a fast procedure anyway. Hour and a half to 2 hours. So it's about time. Of course, endospores are the greatest resistance. You have to have temperatures above boiling. When it comes to vegetative cells, those are cells that are not in the endospore state. Remember, vegetative means active and growing. And it depends. It could be relatively low temperature at 50 degrees Celsius or 60 degrees Celsius for an hour. There's a lot of variations. So we're using a method that's inherently reliable. So whether you're dealing with botulism, okay, a deadly toxin, it's the endospore that's the concern, not the cell. Okay, it doesn't matter whether it's a pathogenistic or a disease-causing organism or not. All of these are very similar in their sensitivity to heat. Not a whole lot of variation. Viruses are resistant, and you can see it depends. I mean, you could have something like that could take 600 minutes at 60. So imagine this. Might be problematic for certain viruses, conceivably naked viruses. I mean, I'm just throwing that out there. Let's see what else I can share with you. And it's based on this, which you don't have to know, where these points are, required to kill all the microbe in a sample in 10 minutes. And the way they've engineered this, they've taken some enormous amount of microbes, theoretically, that you could never possibly have with contamination and figure out the amount of time that's necessary. So the whole idea, a la Pasteur, is to find a way, particularly with perishable agents, whether that's dairy, whether it's prepared foods, whatever, liquids, any consumable, so free of agents of spoilage or disease without affecting the speed or cost of processing. There's a lot of business and commercial related stuff that goes on. I just want to get through this. So boiling water, great. I mean, back in the old days, you see all the old movies. Oh, someone's having a baby, go boil some water. I mean, it's not going to start, but make things as clean as you can. Clean towels, clean everything. All of that. I mean, you can, for many of you at home, that really serves you. I mean, many of you have siblings. I mean, with 3 kids of mine, we're just waiting for who gets the next cut, scrape, mess. And you got to have all that kind of stuff handy. You're ready to deal with these, So as you can see, a single processing and boiling will not kill all resistant cells, disinfection, not sterilization. 30 minutes, non-endospore forming pathogens, including tuberculosis and staphylococci. That might be worth noting. Just retain it. I'm not going to ask you that specific because you have other authors who may disagree. So the trouble is, once you take them out, they get recontaminated. That's absolutely true. But does it make it less useful? No, it makes it still very useful. So those are all the little things. So when you hear, and we get them all periodically, a water boiling type of thing, don't ignore that. Waterborne pathogens are nasty, and most of the time they're going to tell you to put it in and vigorously boil the water for about 10 minutes, let it cool, and drink it. I mean, you're going to clobber almost anything that potentially could, unless there's something specific in that. And every so often you get that, and to that end, certainly I would have a supply of bottled water on tap. Okay. So all of these things, potentially, and there can be problems with this. So between spoilage and illness, it's used all the time. Applies to liquids. It typically applies to liquids. I would indicate to you that it's not just limited to liquids. I mean, you have to be careful with solids with regard to that from a cooking perspective, but retaining the flavor and nutritional value, both important. So things are problems, and this is a very good illustration. This is what a typical small and office autoclave would look. Mine kind of look like that. Okay, probably ours. We have a unit that's considerably bigger than that. The door immediately as you go into the micro lab to the left of it is where we have a big stand-up autoclave. Larger than this. This is a desk or a countertop unit like I had in my office. And you have 3 or 4 trays and you just put stuff in. So you have to be, this is what you use. Glassware, dressings. We use like gauze pads and things like that. Instruments. All the media we make, those are liquids. Paper, you have to be careful with. Okay. You have to let it dry out. We have little peel apart things that'll have plastic on one side and paper on the other. Paper is permeable. You could use a paper bag. But be careful. You have to let it dry thoroughly because that moisture will tear fairly easily. Okay. Those Petri dishes that you use all the time in the lab, that all that media is in, they are sterilized, as you will learn, by gas. And they're sealed in a container. We open them up. And basically, once we grab them, the outside is no longer sterile, but we quickly open them up, pour that hot liquid in, and seal them, and then let the plates cool. That's how everybody pours plates that way. If you're doing it here in a university or someplace, an office where you're making your own plate, most of the labs will buy these commercially done that are there. And again, the autoclave still a good choice. However, ineffective for oils and waxes, things that are harmed by it. It's really an idea. You can read through this. It's more than you need to look at. That's there. This is the incineration nugget. Okay, very good. Bunsen burner. Look how hot that is. Typically, big furnaces or incinerators used commercially. Just destroys it. Hot air ovens work. Okay. It radiates the heat, circulates it. If you have a convection of it, that means you got a fan in there circulating it. Makes it go a little bit faster. I mean, to me, these are more reasonable numbers. Again, I'm looking probably on the top end of that for 2 to 4 hours. In our office, we would normally 20 minutes. If you read all the authors, they'll say that 121 degrees Celsius for 20 minutes is fine. We left it for half an hour. Why not? It wasn't like we had to do 60 of those. We'd have a day after a surgery. If we had 2 surgeries in a day in an office, a small office, that's a lot. So we'd have different packs made up. I'm going to show you that in a second. And what will happen is, hey, and then we get them cleaned off and set up and repackaged. And the next day we do our sterilizing. So you probably were doing surgery in the office 1 or 2 days a week. And in the meantime, prepping all the stuff that you need. That's just the way it ran. And like I said, my first wife as an RN and a BSN taught all of my staff who were not in some basic medical training how to do all that stuff. Make sure everything was done right, how to clean it, how to maintenance for the machines. There's a lot that, whether that's still part of the curriculum, I don't know. She learned that where she worked, and I assume when she was at CCAC getting, way back 53 years ago, whatever. Bless her heart. So you're all familiar with that. Now, I'll flip over to the other PowerPoint. So same deal, same thing. So when you get to that PowerPoint, that's the Nestor PowerPoint, Chapter 5. I have it loaded for you. All of these things I've basically said to you, all there. So you don't have to worry. That's where the numbers came from. Effectively, this is whether it's your Instant Pot or whether it's a big commercial one that they have in a hospital. Water on the bottom, some way to lift this up, so they're not immersed in the water. It doesn't take a whole lot to make steam, and you have this sealed container, just like you'd have a seal on a ship. Which I'm very familiar. When you spin it like in a submarine to make basically a water and air tight seal. Starts to heat up, and there it goes. So there's the flash sterilization. This is interesting. Again, the definition does not include prions. So a prion, 132 degrees is thought. We used to think it was 135 for 4 hours. It keeps changing. You know, when I see the word thought, that means, again, that's code for we don't know. If we don't know, I will not ask you that question. Yeah, or else I'll frame it as true or false prions, are thought to be. And then the answer is almost, it's a permissive term. It's almost always true. Think of that when you're test taking. Permissive terms make it easier to say true. It may do this. Yeah, why the heck not? Test taking. That's all right. So this is this is a significant feature. Using the autoclave, these are called Denison wraps. You're going to see them in the hospital. If you go through a rotation with this, you're going to see them in the medical office. We double wrap. They're wrapped in a particular way so that when you open it at the tape, you can peel it holding the outside and literally flip it on the inside or have someone grab it without contaminating the interior. There's a whole way of folding these things that you will learn. Like if you see that, go back in the lab and look at those sterile blades. It's a peel apart. It's like a wrapper like the sterile Q-tips you use in the lab. You open them up, put your hands away, and you pick them out that way. Got to avoid contamination. It's sterile handling, aseptic technique, particularly in a sense in a medical environment, is like golf. If golfers have to call penalties on themselves, okay? You know that I'm up there and I get that, take that big swing and the ball doesn't. Well, it's a practice swing. So if that ball rolls, if it does something, if you touch it in a sand trap, it's a penalty. Same thing here. If you think you contaminated, guess what? You contaminated. Don't play fast and loose, please. Nobody will know but you, but heaven forbid something bad happens to that individual. That's the kind of stuff that keeps you up at night. So what happens is you double wrap them. They're like a paper bag. They're permeable to the steam. So you always have to have some degree of permeability that steam can get through. Does this mean it's sterile? Here's what happens. You put them on here, you date it, and when they're exposed to a sufficient amount of heat, it has a chemical agent that will darken and create stripes. You will see this in the lab if you look at some of the things that you might encounter in the lab. It does not mean it's sterile. Sterilization is a biological phenomenon. You can't measure it with a chemical indicator. You cannot. All that means is, guess what? It's been exposed to heat for a sufficient amount of time to change colors. That's all. In this case, well, that's just on the outside. What if you put that on the inside? And we do. We put a similar type. We'll put a piece of tape in. We'll put another indicator that will change colors. And it'll tell you the heat got to the inside. It still doesn't mean it's sterile. It's like anything else. You have to rely on the ability of the machine that you're using to be sterilized. We did not do this in the office. We never had any problems with it. But in a hospital, here's what they do. They're making so many of these batches. They typically hold them for 24 to 48 hours before they'll send them to the floor or send them to the operating room. They use this. They use a specific form, endospore former. It's got a fancy name. It's the hardest one to sterilize. It's called Bacillus stereothermophilus. You know that? And what happens, they put a little bit in one of these tubes, and every batch, they autoclave one of these tubes. Okay. When it's done, it's one of those crushable things on the inside that you can smush. It releases a growth media that will, if they're still alive, will cause them to grow. In that media is a chemical indicator, and they'll probably go from this to this. So what will happen is they will then take that little vial of a specific bacteria and effectively see if it grows, and it'll take 24 to 48 hours. They'll see right away if it starts to change color. What that means is there's still endospores that could have grown in that batch. They will have to get that situation fixed. That's part of the documentation that they do in a hospital who's ever run central supply. rarely somebody in your field, but you never can tell where you might be called on to be aware, and you have to document that. Here's batch so-and-so. We confirmed that it passed whatever they called this test, and now we've released it to the floor. Just all that little stuff that you do. Offices don't do it so much, hospitals do. Offices like ours rely on that. Should we have done that? Probably. Were we required to do that? No. So you have to use a biological indicator because sterilization is a biological process. And again, if somebody, you go in another discipline or another teacher here says that means it's sterilized, again, none of that. I said it's really not sterilized. Just it's enough that you'll know and I know. Keep it under your chapeau, my dad used to say. So industrial autoclaves, very large for commercial canning. What you're worried about is botulism. So that one, okay, so they use what they call a 12D. It's as though you had a count of endospores that were 10 to the 12th power. That's ridiculous. That's like you have, a trillion of those. It's not really going to happen. So it's impossible to have that many, so we rely on that. Endospores are, and we don't see botulism, but typically low acidity. And why this is important is if you do canning at home. If you like to do that and put up vegetables and things like that, it depends if you have a garden like we do. We dehydrate more than we do the canning, but we do canning as well. You have to do, it's even more appropriate for people who like to do home brew. All of these things are relevant because if you're doing consumables, you have to follow rigid standards with regard to that. That's there. And so you really have to know what the heck you're doing with these things. Make sure, because you can get yourself into trouble. I'll tell you this again. I think I told you before. One of my students was making meat, basically home brew with a honey base, one of the earliest alcoholic beverages. Okay. And he brought it in. He said, this stuff is growing. And I brought some in and we cultivated it. And guess what? Looked under the microscope, endospores. Sure as shooting, it was botulism, which does occur in honey. And that's why we don't give unrefined. We just basically stay away from giving honey to kids under 2 years old. Just don't. Why? They don't need it. So here's the dry heat nugget and blah, 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 blah. Again, filtration to me is more mechanical. So it would classify as a physical method. There's a lot, there's a lot of improvements in this rather than a standard filter, a la coffee filter or a cellulose filter. We typically see this if you know what the contaminant is likely to be based on your handling. This is how we do cold filtration, particularly for liquids that would not withstand heat, and it's done commercially. And then you're all familiar with these HEPA filters or HEPA filters. So the beauty of that kind of unit for filtration is it's effectively going to take all the bacteria and a fair amount of viruses out of the air. It's very, very useful. You'll see them all the time, whether you're using them at home in a vacuum cleaner or in your HVAC units at home, or more importantly, you're going to see them in a hospital sense. If someone's in reverse isolation, read that, a TB patient, the active tuberculosis, they're coughing all the time. They're going to have an exhaust fan in that room that's going to pull that stuff out. So the risk of them, when someone walks into the room, the risk of that getting out and contaminating. If you will come to learn that tuberculosis is airborne, that's different, okay, than a droplet. Droplets, after about a couple of minutes, drop to the floor. Airborne stay continuously up in the air. That's something we have to be, that's why I have to wear special protective equipment for tuberculosis. There's all these nuances that you will learn about. So, but these are excellent. They're very useful. Pay attention to them. Which brings us to the X-ray and radiation unit, that part of the party. And yes, we use it all the time. Okay. So basically, if you're familiar with the visible spectrum. So you and I, in this relatively wavelengths getting smaller to larger, this is a very limited amount of only 300 nanometers that you and I see, from reds at the higher to blues and purples at the lower. Interestingly enough, if this is where it's located, right in that little niche, it's there. If we increase the wavelength, we get infrared, microwaves, and radio waves. Infrared is useful as a form of heat. Microwaves, very, very useful because they basically take polar molecules, water-based molecules, and water inside of things and accelerate them, and that's how they heat. They're not useful in a laboratory sense or in a sterilization sense. They're just too difficult to control unless you want to just heat something up or reheat something relatively quickly. Okay, infrared, useful. Infrared, we use them therapeutically for people with heat on the surface. Okay. So as a physical therapy technique, they're used. I mean, they're really important because cell phones are based on microwaves. It's kind of remarkable how, this is tech, and I do not understand it. Ask somebody teaching physics, they will help you. Here's our thing. As you shorten the wavelengths, they have bacteriostatic and bactericidal and organismicidal and even entitycidal. So they're very, very useful at destruction. Read that as sterilization, not ultraviolet light. Ultraviolet light is helpful. It stops things growing. So if you think of bacteria, or if you think of fungi, or even think of viruses, it's typically what we call virustatic or bacteriostatic. It is used a lot in contaminated water treatment. It's used a lot in medical offices. When something is exposed, dental offices use it extensively for instruments in between usages, et cetera, for certain things. Okay, nowadays, more things are sterilized than you would think about. But ultraviolet's around a long time. What it does, and you might remember, because we'll reiterate this then, it causes something called thymine dimers. The DNA, where you have two thymines next to each other. Remember, it's A's, T's, G's, and C's. So periodically, you're going to have two thymines next to each other on a strand of DNA, here and here. And maybe you'll have two thymines over here. And what it does is it causes them to bond. And it's as though, and if you think of DNA as a zipper, it's like you've got a zipper, and all of a sudden, oh, what happened here? This zipper's a wreck. I can't. You'd have to put a new zipper in or chuck it. Okay, basically that's what it does. So it's useful, but typically only for things that are growing. When we talk about ionizing radiation, now we're getting into the field of true bactericidal. Ultraviolet is not really it. Okay, and I think that's a poor image for that. X-rays and gamma rays. Go up and look in the lab this week. See those neat little, go into one of the drawers where the scalpels are. You're surely going to see those little containers, those little foil things that have the blades in them. They'll be sterilized by gamma rays. And I can assure you, no one is going to get high levels of radiation measurable in their body from changing a blade. Just saying it. So X-rays do it and gamma rays do it. So commercially, they use these all the time for that. So ionizing radiation, gamma rays, X-rays directly destroys DNA. More so, I think the DNA is the thing that's effective in, yes, cytoplasmic membranes. Also, those toxic derivatives of oxygen. So heat-sensitive material after packaging. They put that blade in there. They put the blades in effectively a specialized container, already sealed. Boom, expose them for however long they have to have. Ensure it's all a shielded room. Once everything is done, and make sure it's clear, you can come in there, take them out. For use on a variety of foods, but this is the problem. I mean, if you see that on your strawberries, oh my God, I'm going to die if I eat those. So understand the perception that a lot of folks have. So, I mean, for consumables, it's not a problem. The only time we see people willing to do that, we have one of those ground meat recalls with E. coli. And if you ever go into the store and you see that they're sort of like cylindrical plastic wrap packages with ground meat in them, in that big thing with all the burgers and stuff, look closely. Most of those, radiation. So people will turn to those when the other stuff gets pulled. Ultraviolet, does it destroy it? Yeah. but not good. We do a lab, and we'll be doing the lab in my lab, and I'm sure they'll do it. I'm pretty confident you'll do it with Dr. Dress. You're going to see we're going to put it and we're going to expose it and have you folks expose it to ultraviolet light. And what's going to happen is all you need to do is like put a 3x5 card or put that plastic top from Petri dish on top of it. It doesn't get through. So thin films or coverings doesn't do well in solids or liquids. Glass, plastic block it. You've got to be careful using it, obviously. And so that's something we do a lab to show the effectiveness of this and how much time is involved. And it's sort of I call it busy work lab, and you look at the results the following week. Then you incubate everything. You mark which side had the covering. That's why I use like 3x5 cards, any kind of cardboard card. And sometimes this is high pressure will do it. So why sort of the appeal? I mean, you don't want to open. I personally make my guacamole. It's very easy. But like yesterday, we grabbed some at the store, and because it's going to go brown if you don't use it quickly. It's I'll be glad to part with the recipe if you like. It's got like 4 ingredients. Okay. 5 avocados, limes, cilantro, garlic, and whatever else you want to put in. Chopped up a little red pepper maybe, and then you can go crazy after that. So this just sort of summarizes all of these things for you. Again, not just filtration, but the mechanical activity of washing your hands is a very, very significant part of this as well. And so we're going to get into the chemicals after this. That chart Disney asked me about a while ago. Let me go back and make sure where we are. And so here, cold we'll talk about. Cold retards growth. It just slows it. So when you're talking about cold, you're really not getting a whole lot out of it. So the big problem with it is there's spoilage organisms grow inside your refrigerator. And if you leave, and you and I all know that if you leave something in the fridge too long, guess what? You're going to see evidence of it spoiling, whether it's pasteurized or not. I mean, that's why they have Best Buy dates on a lot of those products. I mean, you leave that thing of milk or half and half or whatever, sooner or later something bad is going to happen. So we freeze things all the time. So the trouble is with freezing particularly, okay, what happens is cells have water. When the water freezes, it crystallizes. Those crystals penetrate and puncture membranes. That's the source of what we sometimes call freezer burn. You have to handle things properly when you freeze them. If you make something or buy something and you want to preserve it by freezing, you have to do what we call IQF, individual quick freezing. Make room in your freezer, get a sheet pan, put the stuff on it, lay it flat there, wait till they freeze, maybe put a piece of parchment paper on it or wax paper. When it's frozen, take them out. Then they're safe to put into that bag or 2 bags that you might have them to freeze in. When people just throw those things in there, it damages them, and that really allows for those cells and the water in them to penetrate. So they when you defrost them, they're not the same. People have to know how to freeze things that they do and the little tricks they do commercially for freezing. It's the foodie in me that does this. Trust me. So most microbes are not adverse. So what happens is once they defrost, hello, we're back. So we do dry things. We have a food dehydrator. We use it all the time for stuff that we buy or stuff that we grow. And then this is really useful. It's called freeze drying. It's because it pulls out the moisture. A lot of things come freeze dried. We use our bacterial cultures do in the lab, for instance. And that should suffice for today. I think it's everything physical you have to know. We'll start the chemical methods on Wednesday. I'll get that dictation. Someone's going to ask me about it.